One of the most important concepts in chemistry is the concept of the mole. The mole is sometimes called the center or the heart of chemistry because so many chemical concepts require the use of the mole unit. So the first question, of course, is, well, what is a mole? At the very basic level, the mole is a unit, it's a counting unit. And it's a unit that has a specific number associated with it. For example, the word dozen is a counting unit that's associated and means the number 12. The mole is a particularly large number. It's 6.02 times 10 to the power of 23. Well, what's the point of this particular number? The power of the unit is it allows counting of atoms or molecules or ions, etc., which are extremely small entities. It allows them to count them out using mass. Okay, it's somewhat akin, the analogy, if you've ever thought about cotton balls. Now, cotton balls are pretty light, and when we buy cotton balls, it says that there's a certain number of them in a package. And you can think about it, it would not be very efficient if you were a cotton ball manufacturer and distributor to have a person sitting there and counting out 100 cotton balls, putting them inside a plastic bag, and then sealing up the plastic bag. You would not get a whole lot of cotton balls, right? Or if you hired a lot of people, it'd get done faster, but you have to pay them a lot of money. It takes time simply to count things. So instead, if you know how much a single cotton ball weighs, you can do some quick multiplication, figure out how much 100 cotton ball weighs, and simply weigh out that amount of cotton balls without having to count them. Now you might get 1 or 2 extra cotton balls, or you might get short 1 or 2 cotton balls, but the bottom line is that you're going to come very, very, very close to your target number by simply knowing how much it weighs. That is what the mole allows us to do. The mole number allows us to count out a particular number of atoms by weighing them out. Now you may say, well, where does this particular number come from? Why is a mole this particular number? Well, it just so happens is that that number is the number of atoms in 12.00 grams of carbon-12. Now you remember, this is a specific isotope that has 6 protons and 6 neutrons. Right? So if they weigh out exactly 12 grams of carbon-12, that happens to be the number of atoms. What this does, it simply allows us, since we know the mass of 1 proton and the mass of 1 neutron, rather than trying to spend a whole bunch of time figuring out all the math about how many protons and how many neutrons you need in every isotope and converting that number of grams, that would be a very tiny number of grams, you simply use this number as a way to relate the number of atoms that we have to the mass of the atoms that we have. Okay, so the first concept that we need to discuss is called molar mass. Well, what is this? This is the mass in grams of 6.02 times 10 to the 23rd sorry, typo. Okay, so it's the mass in grams of 6.02 times 10 to the 23rd, or 1 mole of atoms or molecules or ions of something. Where do you find the molar mass? It's on your periodic table. Okay. The average atomic mass in grams equals molar mass. So if you take out your periodic table and take a look at some of the elements in the periodic table. So for example, if you look at lithium on the periodic table, the average atomic mass of lithium is approximately 694 atomic mass units. However, if we have 6.94 grams of lithium, that is 1 mole of lithium atoms, which is the same as 6.02 times 10 to the 23rd atoms. Okay, if we looked up aluminum, the average atomic mass of aluminum is about 26.98 atomic mass units, but if we had that many grams of aluminum, we would have 1 mole, or 6.02 times 10 to the 23rd atoms. Now, why does the same amount of lithium atoms weigh a lot less than the same amount of aluminum atoms? Well, a lithium atom, if you look at it, lithium is atomic number 3, and the average atomic mass is pretty close to 7, which means on average lithium atoms have about 4 neutrons. So they have about 7 subatomic particles in their nucleus. Remember, the nucleus is where all the mass, about 99.99% of the mass of any atom resides. Aluminum is a larger atom than lithium. It's atomic number 13, and with an average atomic mass of close to 27, it's got about 14 neutrons on average in the nucleus. So it's got about 27 subatomic particles in the nucleus compared to lithium with about 7. So because it's a larger atom, okay, the atoms weigh more. Okay? It's like having little ping pong balls versus bowling balls. Okay? The same number of ping pong balls will weigh a lot less than the same number of bowling balls. So 1 mole of every atom on the periodic table has different masses because they have different numbers of subatomic particles in their nucleus. Okay, well, so now it's easy to find molar mass of an element. What about molar mass of a compound? What happens if I have something like sodium hydroxide? Well, how much, if I have 1 mole of sodium hydroxide ions, so they're made of sodium ions and hydroxide ions, how much does that weigh? Well, for the molar mass of a compound, you have to count for yourself how many atoms would be in one formula unit, and that would be how many moles of each element would be in 1 mole of the entire ionic compound. Okay. So I tell students it's a little bit like if you have a bicycle, you have 2 wheels for every 1 bicycle. So if you had 10 bicycles, you would have 20 wheels. And if you had 100 bicycles, you would have 200 wheels. And if you had 1,000,000 bicycles, you'd have 2,000,000 wheels. And if I said, well, if you had 6.02 times 10 to the 23 bicycles, which is a mole of bicycles, you'd have 2 times that number for wheels. And if you want to know the mass of a bicycle, and you couldn't weigh the bicycle, but you knew the mass of each one of the parts, you just have to figure out how many of each part is in the bicycle, and then add up the mass of those parts. You're doing the same thing for molar mass. Okay, so we're going to start with NaOH. So we have 1 sodium, 1 oxygen, and 1 hydrogen. That means that in 1 mole of NaOH, it has 1 mole of sodium, 1 mole of oxygen, 1 mole of hydrogen. Now what we're going to do is we're going to multiply these times the molar mass of 1 mole of this element. So sodium is about 22.99. Okay. I'm using a periodic table. It's a little bit different than yours, so my numbers may vary slightly from yours. Oxygen is 15.999. That's in your periodic table. And hydrogen is 1.0079. Okay. So what we're going to do now is we're going to do the sum. For those of you that take a little math, you know that that's sigma, which means sum of. So all I'm going to do right now is I'm going to take my calculator out, and I'm simply going to add those 3 molar masses together. Okay, and those add up to that is 5 sig figs. So that's molar mass of a compound. Let's do another example. Let's do one that's a little bit more complicated. Let's do potassium phosphate. Okay, so this whole thing is made up of 3 Ks, 1 P, 1 phosphorus, and 4 oxygens. So I would multiply 3 times molar mass of K, which is about 39.1. P is 30.97 approximately. And O is 15.999. Okay, I'll reiterate again that I'm using a periodic table. It's a little bit different from the one I normally use in class. So you'll see some minor variations in the molar masses. Okay, so I'm going to multiply 3 times 39.1, that's 117.3. 1 times P is 30.97. And 15.999 times 4 is 63.996. Okay, I'm going to take these 3 answers. I'm going to add them all up. Okay, and this one adds up to 212.27. Now, don't forget, if you're doing something like ammonium sulfate, remember that you have to multiply numbers outside of the parentheses too. So this would have 2 nitrogens, 2 times 4, or 8 hydrogens. And there'd be 1 sulfur and 4 oxygens. Okay, I'm not going to calculate the molar mass for this one. Now at this point in time, you might want to pause the video and practice on your molar mass worksheet, finding the molar mass of compounds. Okay, now that you've had a little bit of practice finding the molar mass of a compound, let's talk about actually using all of these to do what we call mole conversions. So I'm going to do a little diagram, and you might want to put this somewhere in your notes, and you're going to refer to it frequently. Okay, so we're going to start with 1 mole. We can convert between moles and number of particles. which are atoms, molecules, ions, etc. How do we do that? We need to use the number 6.02 times 10 to the 23. You will hear this number referred to occasionally as Avogadro's number. It's named after an Italian chemist from the 1200s named Amedeo Avogadro. Now, he didn't actually come up with the number, but he came up with a concept that we'll talk about in our unit on gas laws that eventually led to the ability to actually calculate and determine the number 6.02 times 10 to the 23rd. Okay, another thing that we can do is we can relate the mole unit to grams of something. Okay, we just discussed that we do this with molar mass. Where do we find molar mass? On the periodic table. Now, one more that we haven't discussed yet is we can relate a certain number of mole to a certain number of liters of gas. Now, this is not liquids or solutions. Okay, this only refers to liters of gas. Well, what's the magical number, if you will, here? It's 22.4. Right? It actually turns out that a mole of any gas, this is only for gases, will occupy 22.4 liters at a certain temperature and pressure, which is called standard temperature and pressure. We'll talk about that in our gas laws unit. For now, you may assume that a mole of any gas will occupy 22.4 liters. Okay, so make sure you have copied this particular diagram down somewhere in your notes, because you're going to need to refer to it when we actually do some conversions. Okay, so to actually convert between particular units, you're going to need to use the factor label method. Okay, so this is an example of the problems that you'll encounter. So you have 7.2 moles of helium, and you would like to know how many atoms of helium does that represent. Well, if you go back up to this right here, moles to atoms requires the use of 6.02 times 10 to the 23rd. Okay, so to set it up, you're going to start with your given number and the unit. This unit right here, you're going to rewrite down here in the box. And you're going to put the number 1 in front of it. Anytime you see the word mole in a conversion factor, not a given amount, it will have a 1 next to it. Well, what does 1 mole equal? 1 mole equals 6.02 times 10 to the 23. Okay. Mole cancels, and I multiply. Remember, anytime we do this, you multiply across and you divide by things on the bottom. So this would be 7.2 times 6.02 times 10 to the 23 over 1. Please don't forget, when you were doing these problems, to use the EE button on your calculator instead of pushing the multiplication button and 10 to an exponent. You're going to end up with some very strange numbers if you try to do it that way. Okay, so I'm going to take 6.02 E23 times 7.2 and my answer to significant figures. Yes, significant figures are back. Okay, there are 2 significant figures here. So my answer originally in the calculator says 4.3344 times 10 to the 24. I have to round that off to 2 significant figures, which means I'm going to round to 4.3 times 10 to the 24. If you do not remember significant figures, you may want to take a moment and go back and review in your notes from the beginning of the course about how to find the number of significant figures in a number and how to round to significant figures. All right, let's do another example here. Okay, so in our next problem, we have 10.3 grams of copper. We'd like to know how many moles does that equal. Okay, remember you're going to always start with your starting value and your units. Okay, I'm going to go back and take a look at my diagram. And this says grams, moles, use molar mass from the periodic table. Okay, this unit here, grams, has to go on the bottom. So this is grams, so this is the molar mass of copper. If you go to your periodic table and you look, it looks like copper is about 63.55 grams. And I'm converting from grams to moles. Remember I said in any conversion factor, the word mole will be next to a 1. It'll be 1 mole. Okay, the grams is going to cancel out. So I'll have 10.3 times 1 divided by 63.55. So 10.3 divided by 63.55 is 0.162077. Well, where do I round that off to? Well, there are 1, 2, 3 significant figures in my given value, so I'm going to need to round that off to 0.162 moles. Okay, so I can do this type of a setup for any type of single mole conversion. When I'm converting from moles to something else or from a different unit to moles. Gets a little more challenging. What if I want to convert from grams to liters? Okay, this is actually 2 steps because I have to go grams to moles and then moles to liters. Okay, so we're going to set this up. Remember, 2-step problems means your boxes are going to have, you're going to have 3 boxes, 1 for your starting ones and then 2 for each of the different conversion factors you'll need. Okay, so let's say we have 79 liters CO2. I'd like to know how many grams that many liters of carbon dioxide would weigh. Okay, so now I'm going to start with 79 liters. Now, since I'm not converting, it doesn't problem to say convert liters to moles. I'm going to have to do liters to moles. It's the invisible step, and then moles to grams. So I'm actually going to need a bigger box. These are sometimes called mixed mole conversions because you have different units that are mixed up together. Neither one of them actually says mole, but you have to do the hidden step. You have to convert to the mole first. Alright, so I know I'm going to have to convert the liters to moles and then the moles to grams. Let's go back to our diagram. Okay, liters to moles. Okay, the number for the conversion is 22.4. Okay, well, where does the 22.4 go? Well, the 22.4 is actually a number of liters. So it goes on the bottom. What goes on the top? Well, it's a mole is 22.4 liters. Okay, but now I have to go to grams. I have to end up converting to grams to my final unit. Okay, so I just converted from liters to moles. Now I can convert from moles to grams. I need the molar mass from the periodic table to solve that problem. Okay, in order for mole to cancel, the mole is on top here, the mole will go on the bottom here. I know it's always 1 mole. So then the next question is, what number goes up here? Well, it's the molar mass. This is a compound, carbon dioxide. So I need molar mass of the compound. So anytime you see a compound and you need molar mass, you're going to have to take the quick extra step. I say I write 1 carbon, 2 oxygens. Carbon is 12.01. Oxygen 15.999. Okay. So 12.01 plus 2 times 15.999 is equivalent to 44.009 grams. That's the number that goes here, the molar mass of carbon dioxide, 44.009, goes on top. Okay, so remember, when you do these, you multiply all the way across the top, so it'll be 79 times 1 times 44.009, and I'll divide that by 22.4. Okay, so 79 times 1 times 44.009, and I'll divide my answer by 22.4. Okay, the calculator says 155.21. So my question is, how do I round 155.21? Sorry, typo. How do I round this? Well, there are 2 significant figures, so I'm going to have to round. This my little symbol means I'm rounding to 2 sig figs. Okay, remember when you round, you can drop off numbers after the decimal. That leaves me 155, but that's 3 significant figures. So I'm going to have to round. Now I'm going to have to start replacing zeros. Okay, I'm not going to start dropping off numbers anymore. I'm going to replace numbers with zeros. Well, I would like to replace the 5 with a 0. Since to do that, I would have to round, since this 5, up to 6. So I would round it off to 160 grams. Alright, let's do one more mixed mole conversion, and then it will be your turn to practice some of these. Now remember, single mole conversions will be just something and the mole in the conversion factor. Mixed mole conversions, you won't see the word mole anywhere in the problem. But you have to convert from the starting unit to moles, and then from moles to the ending unit that you want. Okay, so let's say that we have (7.9 times 10 to the 29 atoms of xenon). Okay, xenon is a gas. I'd like to know how many liters of gas that many atoms of xenon would be. Okay, so again, 7.9 times 10 to the 29 is the first piece. Now, I do not see the word mole. That means it's a mixed mole conversion, which means I have to put the word mole in here somewhere. Okay, this is atoms. So this has to be atoms. Okay, go back and look at my diagram. Atoms to moles, I need 6.02 times 10 to the 23. Okay, so 6.02 times 10 to the 23 atoms is equivalent to a mole. Okay, I got to get to liters, so mole's going to drop down here. Mole. Liters up here. Go back to the diagram. Mole to liters requires 22.4. So it's 22.4 liters, 1 mole. Okay. Now, please note that I didn't need molar mass. Why did I need molar mass? Because the grams doesn't appear anywhere in the problem. So I'm going to take 7.9 times 10 to the 29 times 22.4 and divide that answer by 6.02 times 10 to the 23. Okay, so 7.9 E29 times 22.4 divided by 6.02 E23. Okay, it's a big answer. The answer is 293,953,48.84. Okay, well, let's look at how many significant figures. Whoa, 2. I've got to round that whole thing off to 2 significant figures. Okay, that's going to drop off. Okay, and I'm going to have to replace the numbers before the decimal point with zeros. And then drop off the decimal point. Alright, so this is going to become a 0, 0, 0, 0, 0, 0. Okay, this is 29, okay, but this is 3, so I'm going to round down. So to 2 significant figures, I'll put 29, and I'm going to replace 1, 2, 3, 4, 5, 6 numbers that were before the decimal place with zeros. 1, 2, 3, 4, 5, 6. Well, that's a lot of liters, 29 million liters. Well, turns out that that's a lot of atoms. That's a lot of moles, so it's a lot of liters. Okay, good luck when you're doing these. Remember that if you see grams in the problem, okay, and it's a compound, you're going to have to stop and find the molar mass of the compound. You must show me on your work, you must show me molar mass of a compound. You do not have to show any molar mass for molar mass of an element. And if it's a diatomic element like oxygen or chlorine or hydrogen, you do not have to show me work for simply doubling the molar mass in the periodic table.